Have you ever looked at pictures of those massive ancient stone walls in Peru and just thought, how on earth did they do that?
Oh, yeah, it's wild. It's a logistical nightmare just looking at them.
Right. You know the ones I mean.
Hmm.
You see tourists standing next to these walls in Cusco, and they're just dwarfed by single stones that weigh like over 100 metric tons.
And they aren't uniform blocks either. They aren't like modern bricks.
No, not at all. They are cut into these wild, irregular, multi-angled shapes. Yet they fit together so perfectly that you couldn't even slide a piece of paper or, a razor blade between them.
Which is just incredible craftsmanship.
It is. And for decades, the traditional accepted story has been one of sheer mind-boggling brute force. We've been told that ancient people somehow dragged these mega boulders across the rugged Andes Mountains, hoisted them into place, and then just meticulously chiseled them by hand to fit flawlessly against their neighbors.
Which, when you really think about it, just doesn't hold up.
Exactly. And that's our mission for today's deep dive. We're going to explore a paradigm-shifting 2026 material science paper by researcher Trevor Hawke. We're going to take this highly complex study and break its mind-bending conclusion down in the simplest way possible.
Yeah, and the conclusion of this paper completely dismantles the conventional timeline of Andean megalithic architecture.
Because that conclusion is basically this. The ancient builders didn't carve those stones, they poured them, like concrete.
Right. The paper is called Evidence of Geopolymer Concrete in Megalithic Architecture of Cusco, Peru. And it provides this massive convergence of forensic, chemical, and historical data.
Which is so much better than the old theory. The logistics of the traditional carving theory always bothered me.
Oh, absolutely. It's nearly impossible.
Imagine trying to hand-carve a 100-ton jigsaw puzzle piece so it perfectly matches the complex angles of the stone next to it. To check if your carving is right, you'd have to lift 100 tons of rock, lower it to check the fit, see where it rubs, lift it back up, carve a millimeter off, and repeat that process hundreds of times.
Right, and doing that on a steep mountainside borders on the absurd.
Exactly. But if you just build a temporary mold right next to the previous block and pour a liquid plaster into it, the liquid naturally fills every single microscopic contour of its neighbor. One method is a logistical nightmare. The other is just applied chemistry.
Well said. And to really appreciate the magnitude of what Hawke's paper reveals, we have to look at the specific sites, like the fortress of Sacsayhuaman and the Qorikancha temple in Cusco.
These are real architectural marvels.
Oh, totally. I mean, they have withstood massive tectonic activity and severe earthquakes for centuries. And they've done it without a single drop of traditional mortar holding them together.
Which brings us to the solution. The concept that solves this puzzle was actually pioneered decades ago by a materials scientist named Joseph Davidovits. He introduced the world to something called geopolymer concrete.
Yeah, geopolymer concrete. It sounds like something from an aerospace lab, right?
Yeah, not a 500-year-old ruin in the Andes.
Yeah.
So translating that into everyday terms, we're basically talking about creating artificial stone.
Exactly. You start with natural volcanic rock, like volcanic ash or tuff, which is super abundant in that region. You break it down, and then you mix it with a highly alkaline liquid.
And what does that liquid do exactly?
That highly alkaline liquid acts as an activator. So when you mix it with the pulverized volcanic rock, it triggers a reaction called geopolymerization.
Geopolymerization.
Yeah.
Okay, so it changes the chemistry.
Yeah. In simple terms, the high pH of the alkaline solution breaks the silicon and oxygen bonds in the natural rock. It literally turns the solid material into a malleable slurry.
Wow. So they melt it down.
Basically, yeah. And as that slurry cures at room temperature, those molecules reassemble into a three-dimensional network. It hardens into this incredibly dense, ceramic-like cement.
But it still looks like rock.
That's the crazy part. To the naked eye and even to basic geological tests, it looks and feels exactly like a natural volcanic rock.
See, I have to admit, when I first read that, my inner skeptic immediately flared up, and I imagine anyone listening might be thinking the exact same thing.
Oh, for sure. It's a big claim.
Right. If I walk up to a wall and look at a rock, it just looks like a rock. How can a material scientist in 2026 look at a 500-year-old wall and definitively prove, beyond a shadow of a doubt, that it is ancient concrete and not just a giant boulder dragged from a quarry down the road?
Well, the answer lies in the fundamental difference between natural geological formation and human engineering. When you engineer an artificial concrete, you leave behind chemical signatures that natural, earth-made rock simply does not possess.
Chemical signatures.
Right. And in the case of the Qorikancha temple in Cusco, Hawke's team didn't just find microscopic signatures, they found macroscopic evidence literally sweating out of the stones.
The sweating walls.
Yeah.
When I saw the photographs in the study, it clicked for me immediately. It's a process called efflorescence, isn't it?
Yes, exactly. Efflorescence. Hawke's research team went to the Qorikancha temple and focused on the underside of a massive lintel block over a doorway known as Door 1.
Okay.
And they found this white, crusty mineral deposit accumulating on the surface of the stone.
I instantly recognized it because it's the exact same powdery white water stain you see on the cinder blocks of a damp, unfinished basement.
That basement analogy is the absolute perfect way to understand the mechanism here. Because geopolymer concrete, unlike solid igneous rock, has a mesoporous structure.
Meaning it's porous.
Yeah, it is full of microscopic interconnected pores. So when environmental water, like rain or humidity, penetrates the stone, it travels through that porous network.
Okay, that makes sense.
And because the geopolymerization process requires a massive amount of alkaline chemistry to cure properly, there are often excess salts left over in the matrix, specifically calcium carbonate and sodium carbonate.
So the water acts as a transport system.
Exactly. It dissolves these excess salts, carries them through the microscopic pores to the surface of the stone, and when the water eventually evaporates, it leaves the salts behind as a visible white crust.
But natural volcanic rocks, like the andesite and diorite that these walls are historically assumed to be made of, they don't do that. You don't see natural boulders in a field just sweating out massive amounts of alkaline salts.
Oh, you really don't.
But the Hawke team took it a step further, which is my favorite part. They waited until dark, brought a high-powered 365 nanometer ultraviolet blacklight to the temple, and shined it directly on those crusty white spots.
Yeah, and the results were stunning.
Those spots glowed a bright phosphorescent green.
Yeah.
I mean, I have been hiking in the mountains many times. Natural rocks do not glow under a black light like a velvet poster in a college dorm.
No, they definitely do not. And that glowing is the true forensic smoking gun of this section of the paper. It all comes down to trace radioactive elements.
Wait, radioactive elements? Like what?
Specifically uranium and thorium. These elements exist naturally in the Earth's crust, but in a natural, solid volcanic rock, they are locked firmly in place within the crystalline structure.
Okay, so they can't move around.
Right. However, when you pulverize that rock and subject it to a highly engineered alkaline chemical bath to create geopolymer concrete, those trace elements become highly mobile.
So as the water pushes the leftover salts through the pores to the surface, it drags these trace radioactive elements along for the ride.
Exactly. It acts as a chemical conveyor belt. The water transports the uranium and thorium to the surface and concentrates them in those specific efflorescent spots.
Oh, wow.
And when you bombard those concentrated elements with ultraviolet light, the radiation excites the electrons, causing them to fluoresce or glow green.
That is wild.
Right. If that lintel block were a solid, natural, non-porous stone carved from a mountain, those elements could never have migrated to the surface in the first place. The migration itself is absolute proof of an engineered, porous silicate matrix.
Seeing a stone sweat salts and glow in the dark is incredible visible evidence. But to really prove this was poured, we have to go deeper than the surface. If you're investigating an ancient recipe, my instinct is to chip off a piece and put it under a microscope to see what ingredients were actually used.
And that is exactly what the researchers did using energy dispersive spectroscopy, or EDS.
Right, EDS.
It's a vital tool in material science. You bombard a sample with a focused beam of electrons or X-rays, and the sample emits its own X-rays in response. By measuring the energy of the emitted X-rays, you can determine the exact elemental makeup of the material.
So what did they find when they analyzed the samples from Cusco?
Well, first they looked at the levels of potassium. To create the highly alkaline solution necessary to melt the volcanic rock, the ancient builders would have needed a strong reagent.
Like a chemical catalyst.
Right. And the most logical source in the ancient world was plant ash, which is incredibly rich in potassium.
I instantly thought of the old-fashioned method for making lye soap when I read that.
Yeah.
You don't just find lye in nature, you have to engineer it.
Exactly. It's a process.
You take hardwood plant ash, run water through it, and you get a highly alkaline potassium hydroxide solution. Just like that lye breaks down animal fats to create soap, this highly alkaline plant ash mixture literally breaks down the chemical bonds of the volcanic rock.
Yeah.
It turns solid stone into a malleable paste.
Right. So if they used plant ash to melt the rock, the chemical signature of that ash should still be there.
And does the EDS data confirm it?
It confirms it spectacularly. The temple walls showed a massive 109% increase in potassium compared to the natural volcanic rocks found in the local quarries.
109% increase. A natural stone does not magically double its potassium content between the quarry and the building site.
Or no, it doesn't. The only scientific explanation is the intentional manual addition of a potassium-based reagent during a manufacturing process.
So the recipe is openly revealing its ingredients. But it's not just the ingredients, it's the exact proportions. I was reading the section on the mathematical ratio of silicon to aluminum.
Yes, the Sial ratio.
Right. Because in modern geopolymer science, achieving structural strength isn't just about throwing things in a bucket. It requires serious precision.
Absolutely. Getting the silicon to aluminum ratio correct is the difference between a cement that crumbles in your hands and one that lasts 1,000 years. Modern material science dictates that an Sial ratio between 2.0 and 2.5 is the absolute sweet spot for maximum structural strength and weather resistance.
And where did the Hawke samples fall?
When the Hawke team measured the samples from Cusco, the ratios fell between 2.17 and 3.12.
Wow, so this isn't just a random agglomeration of dirt.
Not at all. It is mathematically optimized for high compressive strength. It is a chemically synthesized material engineered to exact standardized specifications.
Even with all that complex chemistry and optimal ratios, there is one detail in this paper that is so delightfully simple and undeniable that it completely shuts down the carving theory.
Oh, I know what you're going to say.
The researchers found what I like to call a bug in the amber. In the paper, they refer to sample 2B.
Yeah.
When they placed this piece of the ancient wall under a scanning electron microscope, they found a fully fossilized microinvertebrate.
Yes, a tiny ancient soil bug.
Completely encased and seamlessly integrated into the solid matrix of the stone.
The presence of that microinvertebrate is the ultimate thermodynamic proof, because we have to consider how natural volcanic rock is actually formed.
Right, from a volcano.
Exactly. Igneous rock, like andesite or diorite, is forged in the belly of the earth from magma. We are talking about temperatures exceeding 1,000 degrees Celsius. Any organic matter, whether it's a leaf, a piece of wood, or a microscopic soil bug,
Would be instantly and utterly incinerated.
completely. It wouldn't even leave ash. It would be vaporized.
So finding an intact, fossilized bug trapped deep inside the structure of this rock proves beyond any doubt that this material did not form inside a volcano.
Right. It transitioned from a liquid paste to a solid stone at normal, everyday environmental temperatures.
It's the ultimate proof of cold mixing. The builders mixed a batch of geopolymer concrete, maybe in a pit or a trough, and this poor little microscopic bug just happened to be in the wrong place at the wrong time and got scooped up into the slurry.
Exactly. That fossilized bug really shuts the door on the natural stone argument. But, moving from the microscopic to the macroscopic, if this was wet concrete poured on a massive scale, we should expect to see physical evidence of that fluid behavior with our naked eyes.
Right, because 100 tons of wet poured stone is going to behave very differently than a block of carved rock. It's subject to fluid dynamics.
Exactly, and that brings us to the famous pillowed stones at the Sacsayhuaman fortress.
I love this part. When you look at pictures of these walls, massive stones bulge outward at the center. They look soft, almost like giant stone marshmallows squished and stacked on top of each other.
Yeah, that's a great description.
And for generations, historians have argued this was a deliberate stylistic choice, that the ancient builders painstakingly carved a convex bulge into the face of every single block for aesthetic reasons.
Which is just wild to think about.
Right. If you're already fighting a logistical nightmare to just cut and move a 100-ton rock, why on earth would you add hundreds of hours of extra unnecessary labor just to make it look puffy?
The short answer is you wouldn't. The Hawke paper brilliantly explains this pillowing effect through the lens of non-Newtonian fluid dynamics.
Okay, break that down for us.
Sure. So when you pour a massive volume of wet geopolymer concrete into a mold, it's incredibly heavy. A non-Newtonian fluid changes its viscosity depending on the stress applied to it. In this case, the sheer gravitational mass of 100 tons of curing paste pushes outward against whatever temporary mold or framework the builders erected.
So before the chemical reaction fully hardens the paste into ceramic, it slumps.
Exactly. It bulges outward under its own weight. That pillowed look isn't a stylistic carving choice. It is the natural physical result of gravitational slumping and a massive liquid pour.
The physics dictate that it has to bulge. And the physical evidence of manipulation doesn't stop there. I found the section on the Inca Roca Palace fascinating.
Oh, because of the trowel marks.
Yes, they actually documented visible trowel marks on the exterior faces of the stones. Troweling is a very specific mechanical finishing technique.
Right, like when you pour a modern concrete sidewalk, the workers use a flat tool to smooth the wet surface, consolidate the material, and push the aggregate down.
Exactly. And you can literally see the sweeping, overlapping patterns where an ancient worker smoothed the surface of the wet stone paste before it hardened. Natural volcanic rock formed by cooling lava simply does not feature sweeping trowel marks.
No, it definitely doesn't. Trowel marks are undeniable evidence of plasticity at the time of construction. But perhaps the most misunderstood visible features of these walls are the strange protrusions.
Oh, the knobs?
Yeah, anyone who has ever looked closely at the walls in Cusco has noticed these random, irregularly shaped knobs or bumps sticking out, usually near the bottom of the stones.
And for a long time, the prevailing archaeological theory was that these were lifting bosses. Knobs intentionally carved so workers could tie ropes around them to hoist the blocks into place.
Which is another theory that kind of falls apart under scrutiny.
I've always struggled with that one because it makes zero physical sense. If you want to lift and balance a 100-ton object, you don't put the lifting point at the very bottom edge. It would just flip over.
Right, the center of gravity is all wrong.
Plus, they are irregularly shaped and often sloped, which would make them terrible for securing heavy ropes. So what purpose do these knobs actually serve if they aren't for lifting?
Well, the paper identifies them as syneresis drainage ports.
Syneresis drainage ports. Okay, what is syneresis?
Syneresis is a process in chemistry where a gel or curing paste expels liquid. When you are mixing geopolymer concrete on a megalithic scale, controlling the water-to-binder ratio is incredibly difficult.
Okay, so if you have too much water.
Right. If you have excess water or excess liquid alkaline solution, that liquid needs a way to escape so the block can cure and harden properly without cracking.
And because gravity pulls everything downward, that excess liquid naturally migrates through the wet paste to the absolute lowest possible point in the mold.
Precisely. The ancient builders completely understood this. They intentionally created these little protrusions at the bottom of their molds to act as exhaust ports or drip spouts.
That is so smart.
It allowed the excess water and chemical runoff to safely leak out of the curing block. And the Hawke team proved this by taking their UV blacklight back to the walls.
Oh, did it glow?
The most intense, bright green, glowing efflorescence, the heaviest concentration of those migrating radioactive trace elements, was found heavily concentrated right underneath these specific drainage knobs.
Wow, so the highly alkaline chemical water literally drained out of those exact spots, leaving the fluorescent signature behind.
Exactly.
The concept of pouring the stones perfectly explains the most famous feature of all, too, the gapeless joints.
Right, the razor blade test.
Exactly. The reason you can't slide a razor blade between 200-ton rocks isn't because an ancient stonemason possessed superhuman carving abilities. It's because it was a sequential casting process.
Yeah, it's so much simpler when you look at it that way.
You build a mold and pour block A. You let it cure and harden. Then you build the next mold right next to it and pour the wet paste for block B. The heavy liquid mass of block B naturally flows into every microscopic contour, every tiny bump and groove of the already hardened block A.
And when it cures, you have a perfectly gapeless joint on a megalithic scale, achieved entirely without modern laser cutting tools.
It is such an elegant, highly efficient engineering solution to an otherwise impossible logistical problem.
It really is. But this raises an important point. If the Incas, or the cultures that predated them, possessed this incredibly advanced understanding of chemical synthesis and fluid dynamics, we should expect to see some corroborating evidence in the historical or cultural record.
Yes, and this is where the hard material science intersects with anthropology in a really compelling way. I loved this part of the deep dive because the clues were always there, hidden in plain sight.
Right, let's look at the historical accounts. When the Spanish chroniclers arrived shortly after the conquest, they documented what they saw.
Yeah, in 1553, a chronicler named Pedro Cieza de Leon stood in front of these exact walls. He was so astounded by the precision of the joints that he wrote down that the stones appeared to be joined by a bitumen or liquid, even though there was no visible mortar.
He looked at the wall, and his brain intuitively recognized the visual signature of a poured liquid. He documented exactly what his eyes were telling him.
But the evidence within the indigenous Quechua language is even more profound, right? Language is such a vessel for cultural memory.
It really is. The researchers point to an ancient Quechua term, lancacopa,
I actually looked up the etymology of that term because it sounded so specific. It translates directly to sticky clay, or clay that works.
which is incredibly telling.
Right. That isn't a phrase you use to describe a solid, unyielding mountain boulder. It is the perfect literal description of a high-viscosity, wet geopolymer cement slurry before it cures into stone.
It describes the material state perfectly. Furthermore, early colonial dictionaries translate another ancient Quechua word, tiki, as compacting or stuffing, specifically in the context of masonry and building walls.
You cannot stuff or compact a carved 100-ton solid rock.
No, you can't. But you absolutely stuff and compact wet, sticky cement into a wooden or earthen mold to ensure it fills all the gaps and pushes the air bubbles out.
That makes perfect sense. And beyond the vocabulary, the Andes are rich with deeply rooted oral legends describing ancient builders who possessed a special plant extract that could literally soften or melt stone.
The way these different fields of study lock together is incredible.
It really is. And this is a great reminder for you listening right now. When you are trying to solve a complex problem, whether you're troubleshooting an issue at work, developing a creative project, or just trying to understand the world, don't look at the raw data in a vacuum.
Exactly. Look at the language, the history, the cultural context.
The answer is almost always sitting right there at the intersection of different disciplines. The material scientists found the massive spike in potassium from the alkaline region, and the anthropologists found the local legends about plant extracts melting stone. The chemistry perfectly validates the oral history.
It is a beautifully synthesized argument that really forces us to reevaluate the entire socioeconomic structure of the ancient Andes.
Because these builders were not just managing brute force labor.
No, they were operating a highly sophisticated, empire-wide logistical supply chain. They utilized the massive Incan road system, specifically the Coliseo Road, not to drag finished 100-ton blocks, but to transport the raw chemical ingredients.
They moved volcanic tuff from the quarries, alkaline plant ashes from the forests, and aggregate sands.
Right. They brought the dry ingredients to the building site, mixed the liquid stone in batches, and cast these megalithic wonders directly in place.
And the final result of that chemical mastery was a modular, perfectly interlocking, earthquake-resistant architecture that has easily outlasted almost everything built by the European colonizers who came after them.
It completely redefines our understanding of ancient ingenuity.
So as we wrap up today's deep dive into Trevor Hawke's 2026 paper, what is the ultimate takeaway? Where does this science go next?
Well, the paper concludes with a clear directive for the future. While the chemical, visual, and historical evidence at the Cusco sites is overwhelming, to prove that geopolymer casting was a universal standard across the entire Incan Empire and possibly older Andean cultures, we need to apply this testing methodology to more sites.
Makes sense.
And crucially, Hawke argues for the use of even higher resolution analytical tools, specifically transmission electron microscopy, or TEM.
TEM. Now, unlike the scanning microscopes used to find the fossilized bug, TEM operates on a completely different level of resolution, right?
Oh, completely. It transmits a beam of electrons entirely through an ultra-thin specimen. It allows scientists to look past the microscopic level and actually observe the nanoscale structures.
Wow. So what would they be looking for?
They could map the exact crystallographic orientations. They could literally see the atomic bonds and the polymer chains formed by the geopolymerization process.
Applying TEM to these megaliths would provide the final undeniable mathematical proof of chemical synthesis at the atomic level.
It would allow us to perfectly reverse engineer the exact chemical reaction that took place 500 years ago.
Think about the implications of that for a second. Think about what else might be hiding in the molecular structures of ancient monuments around the world, just waiting for us to point the right electron microscope at it. If the towering, impossible walls of Peru were poured like concrete, what about the massive stone blocks of the Great Pyramids in Egypt? What about the monolithic statues of Easter Island or the heavy stone temples of Mesoamerica? We look at the past and assume it was primitive, defined entirely by simple tools and backbreaking labor. But what if it wasn't? What other impossible ancient mysteries are actually just lost chemical recipes waiting for you to discover them?